the last test. This is the 8th, as we just found out. We went through them all. This is the 8th test. This is the ratio test. Now, the ratio test has some conditions too, and we'll talk through them. And 223 is where we're going to be if you would like to have your book open. So the box on page 23, I'm just going to release part of it at a time, okay? The thing that's really nice about the ratio test is it's very useful for super ugly expressions, super ugly functions with factorials in them, with crazy exponents in them. This test comes in the handiest for that. So like I said, at the end, when we put all the tests together and we say, okay, how do I know which test to use when? Because on the exam, they're not going to tell you which test to use. We've got kind of a list of things to look for. All right, so the next part is there's sort of three if parts, three results that you can have for the ratio test that give you good information. The first part is if our function will converge, our series will converge if the limit as n approaches infinity of the absolute value of the next term divided by the current term is less than 1. And why this next term idea and the current term idea are important is because when we have powers, when we have factorials, lots of stuff cancels out, and we have the ability to easily evaluate these limits. Okay, if it's less than 1, if this setup is less than 1. So the one thing that's nice, and compared to what you guys did with the limit comparison test yesterday, is that keep, change, flip thing is still going to be in play. And so it's going to make simplifying some very, very ugly expressions really not too difficult. So if it's less than 1, it converges. Now, next, if it's greater than 1 or is equal to infinity, then it diverges. Okay. What case is missing? Equals 1, okay? If it equals 1, the ratio test is useless. It is inconclusive. So if you choose to use the ratio test, which I'm going to go through an example of one today where it does equal 1, then if that doesn't work, then you have to try something else. Okay? Those are the three cases. Less than 1, greater than 1 or infinity, or equal to 1. Okay? We're just going to go right into examples. Okay, so here's what I'm talking about. Some pretty ugly looking things. And these really aren't that bad compared to the ones we're going to go over next. So I have a series from n equals 0 of n factorial over 3 to the n. And the second one is 3 to the n plus 1 factorial over 4 to the n times n squared. Now, there's elements of this that feel geometric, right? I've got a little 3/4 going on over here. I got a 1/3 going on over here, but I have an added element that takes that out, okay? So here's how the ratio test works. What we have to do is, first off, be able to talk about, we're going to end up multiplying by the reciprocal of this because the numerator is the next term. Well, the next term means we're adding 1 to n. Whatever our n is, we're adding 1 to it. So what this setup looks like is instead of being n factorial, it's n plus 1 factorial. Instead of being 3 to the n, it's 3 to the n plus 1. And then this is just a reciprocal because when I divide by a fraction, keep, change, flip. Okay. Now, one of the things that I mentioned at the beginning is that, okay, stuff is going to cancel. And I'm going to work through some of this with you because I know you're not completely comfortable with factorials, like it's the back of your hand kind of thing. So let me just kind of show you how this will work and how stuff will cancel out. All right, so to start with, let's focus in on this n plus 1 factorial, right? Because this is really, I'm going to write it down here, n plus 1 times subtract 1 times n minus 1 times n minus 2, etc. Okay, so that is this. Okay, and then of course on the bottom here, I have this is really n times n minus 1 times n minus 2, etc. So we see we get this canceling. I'm going to move this one, actually. No, I guess not. There we go. Now it should be fine. Okay, so that's that blue. So what you can see here is that basically everything cancels, right? When I get down to the n, and everything cancels out. So I'm just left with this n plus 1 on top. So that's what I was talking about when things cancel. Now we can kind of do the same thing here. This is really, when I have, so I'm going to isolate this. So this is 3 over n, 3 to the n plus 1. Again, I don't know why I can't write 3's. So what's the rule? What do we do? All right, now, actually, I'm not going to do it that way. Let's think about it like this. 3 over n, this is the same as 3 over n times 3, right? Because when you multiply and the bases are the same, you add the powers. And so these cancel out, and I'm left with just a 3 down on the bottom. I mean, if you think about the subtraction rule, it ends up being 3 to the negative 1, which is 1/3. So this is what I'm talking about, why the ratio test is nice. We started off with something fairly ugly, and it simplifies down to something pretty easy to deal with, right? Because what is the limit of this? As n approaches infinity. Infinity, right? This is infinity. And in our rule, which again is also greater than 1, whatever, we don't have to say that. I want to get rid of that. I don't like that. Because our rule, it has to either be greater than 1 or goes to infinity, right? And I know we think about infinity as the giantest number you can think of and then just go bigger than that. So of course that's greater than 1. So in some ways, is the second criteria redundant? I suppose. But again, remember, infinity is not a number, it's an idea. Okay, and so what does that mean? Does it diverge or converge? Diverge, okay. So diverges by the ratio test, and that's all you have to say. When you get going with more of these ratio test one and you start getting the feel for the powers and the factorials, these actually end up becoming fairly simple. Okay. So this next one, now here's the thing that's different. Since I already have an n plus 1, what is the next term going to be? 3 to the what? N plus 2. And then I'm going to have 4 to the n plus 1. Now, this n has to change too. So this becomes n plus 1 quantity squared. And then I just flip it for the other side, right? So that's all that I have here. This is, again, the original a sub n flipped, because when you divide by fractions, keep, change, flip. This one is I've just increased the n's by 1. That's how we find the next term. All right? And so now what we should be able to think is, okay, just like we did with this 3n to the n plus over the n plus 1, you know, I'm going to have a 3 on top and I'm going to have a 4 on the bottom. Because there's one more 4 being multiplied. That's what it really means. 4 to the n means multiply 4 by itself n times. Well, this means multiply 4 by itself n times and one more time. So, in other words, one more 4 is included down here than here. One more 3 is included here than here. And so I'm left with this n squared over n plus 1 squared. And whatever the numbers are, okay? So here's where I'm at. I've got one more 3 on top. I got one more 4 on the bottom. Now let's evaluate what's going on here. What is all of this? When n goes to infinity, what happens with these variables? What happens up top here? Yeah, this goes to infinity. This goes to infinity. So we can think about them like a canceling out. So the limit of this is what? 3/4. Yeah. The limit of the variable part is 1, but then I still have this 3/4. So this goes to 3/4, which is less than 1. So therefore, this converges by the ratio test. So these are the simple cases, right, where we don't have inconclusive, where The math and the algebra is not that horrible, okay? Now I understand. You're not completely familiar with this whole next term thing and how to work with that with factorials, but you're going to get better at it because as we practice it, you're going to see this happen and come up more and more. All right? Questions so far? Now, in this particular problem, it actually didn't even ask us to which test to use. So you could have tried a different test. But one of the takeaways, one of the things I'm charged with is trying to get you to zero in on when to use what test. And so again, the key with the ratio test is when we see factorials, that's a sign to probably use it. When you see factorials and powers combined together, that's also a sign to probably use it, okay? But one of the things that you'll find out is you might try a test and you get inconclusive and you got to try something else. And so that's part of my charge to help you work through that. All right, so here are some, number 4 is super ugly, and there's some notation there that is really challenging, and we'll talk about it in a second. Just so you know, this is just expanded out. Okay, this is not 2 problems. This would be the problem, but the double factorial is a new notation for you. There's no reason that you would know what that was. Since with the ratio test, we talk about the absolute value. I mean, what kind of series is this? It is alternating, right? Our negative 1 to the n tells me that's alternating. And so we're going to use the ratio test. I'm going to go through that. But usually, when you have something with alternating, that should tell you, maybe I should consider the alternating series test. Maybe that'll work. But we're going to go through it with the ratio test just to get you used to stuff, okay? So again, I've got to increase n by 1, and when I increase this n by 1, it cancels with the minus 1. And since it's in the absolute value, we're going to disregard this negative 1 to the n completely. All right, so when I increase this by 1, increase this by 1, it just becomes n. Flip this over. How about the limit of this? Did you figure it out? Figure out the limit of this. If you haven't done that yet, do that. As n approaches infinity. What say you? Limit is what? Uno, correct. It's 1. See, I'm just afraid to write equal signs now. Do you see what's happening? What's happened to me? I've turned into being afraid to write equal signs, which can't get you in trouble.
On stats, you write arrows.
It can't get you in trouble if you do that. I got to be honest. And even though it absolutely equals 1, I'm scared to do it now, apparently. And I'm not even taking the exam like you guys. Just trying to set the example for you. All right, yeah, it goes to 1, which means the ratio test is useless. Does not help us at all. Okay, so let's go back to what I had said at the beginning, right? It's alternating. Are they getting smaller as n gets bigger? Is it decreasing? Because maybe we need to use the alternating series test. Yeah, it's decreasing because as n gets bigger, this bottom grows faster than this since it's under the square root. So this bottom is growing faster, which means the bottom is getting bigger, which means the fraction is getting smaller as n increases. Notice how they started at n equals 2, by the way, so we didn't have a 0 to begin with. So that's good. Now, what about the limit of this as n approaches infinity? What's it approaching? It is approaching 0 because, I mean, if we think about this as n to the 1/2, the degree is bigger on the bottom. So we've got all those. First off, the ratio test is inconclusive, useless. We're moving on. Yes, you do. Or what you could do is just sort of exit out and you go, I got to try another test because this didn't get me anywhere. If you come up with something on the exam. Now, that being said, I think this is good. I think this is good evidence to try. Again, we've got powers. We've got radicals. It's kind of funky. Again, the limit of this we just decided was 0. So that's good. It meets all 3 criteria for alternating series tests, which means, does it converge or diverge? It converges. It converges by the alternating series test. All right, let's get into this last one because it's goofy. And this is an odd notation. I shouldn't say odd, because you'll see why I shouldn't say odd in a second. An irregular notation, I'm going to say it that way. What this notation means is it means instead of, for normal factorial means every integer below that, right? One less, okay? This notation means every odd or even integer below that. And so what you have to decide is, do I start with an odd or do I start with an even? Okay, and so 2n plus 1, is this odd or even? It is odd, right? Whenever I plug an integer in, I get some even number and I add 1 to it. So these are, in this case, these are all odd numbers, and you can see they expanded it out for us. So instead of subtracting 1 every time, you subtract 2, because we're skipping the even number in between, right? So this is odd, then we go to the next odd. Subtract 2 again, we go to the next odd. Subtract 2 again, we go to the next odd until we get down to 1. That's what that double factorial sign means. Odds or evens, not both. With the regular n factorial, of course, that's odds and evens, all right? So that's what that kind of looks like, and you think, okay, well, if I look at the next term, think about it that way, as the next term, okay? The next term is not 2n plus 2, it's 2n plus 3. So if I add 2 to it to see another term in front of it, it would be 2n plus 3. So and here's why that's important. So first off, when I have my original that I flipped over, that's this, just flipped over. So when I go to the next term above this, it's 2n plus 3. This is still the same. Oh, let me explain where this came from. Okay, this right here. All right. So this would be, so since 2n minus 1 is the term that we started with, we have to go like this. That is the next term. Right? So when I sub in the 2n, when I sub in the n plus 1, it goes right in here for n. And when we simplify this, this is 2n plus 2 minus 1. So that's how we arrive at this right here. So because right here, the next term is n plus 1, and this 1 is outside of this multiplication. That's why I have to put the n plus 1, I sub in here, and it's getting multiplied by 2. Then I just distribute and simplify, okay? One of the things that it looks like I went to the next odd number, and that's not kind of a rule. That just worked out for this particular problem because there was a 2n minus 1 down here. And it's because of this that's why that happened, okay? Does that make sense? All right, here is still the n plus 1 factorial. Now we got to get on to figuring out how to cancel all this stuff out, because that's what's supposed to happen. Things are supposed to cancel. So let's take care of the easy stuff first. I'm going to get rid of this just because I'm going to use that real estate to show you what I mean. Okay. Now, to be honest with you, canceling these two are pretty easy. Like if I look at this and I look at this, right? This is 2n plus 3 is the term, the odd term right before that. So when I cancel these out, this just gives me 2n plus 3, that term, all right? Hopefully by now we've figured out that when I cancel the 3n and the 3n plus 1, I'm going to end up with a 3 on the bottom. And same with the n plus 1 and the n factorial. I'm going to end up with an n plus 1 on the bottom because it's going to cancel because the next one down is n, and they cancels. This is like n plus 1 times n factorial. And now this one is where it gets a little trickier, but actually, let's write this out. So I've got the limit as n approaches infinity. And so I have 2n plus 3 on top. And then on the bottom, I have a 3 and an n plus 1. I gotta figure out how to deal with this 2n minus 1 and this 2n plus 1. Actually, no, I don't. Let's go like this. Let's just make this. I'm just going to leave this like this. You'll see why in a second. And then this is going to be 2n plus 1. I'm just going to leave all that. What do we know about the degree of the top compared to the degree of the bottom, generally speaking? What is the degree of the top? 2, right? I'm going to get an n squared out of here somewhere, right? What about the bottom?
2.
Yeah, it's also degree 2. It's both n squared. So here's what's important, right? When you take the limit approaching infinity, and this is where this is where having an AB background helps. In reality, since the degree on the top and the bottom are the same, I just need to worry about the leading coefficients, right? And so when I go ahead and do that multiplication, I'm sorry? Which ones? Oh, do you want that there? I can put that there. I don't think it's necessary. Okay. Oh, you're thinking the 3. Yeah. Okay, I'm with you. I'm with you there. Thank you for that. Okay, so when we talk about that, we just have to talk about the leading coefficients, right? In reality, I have 4n squared that I have to worry about. There's other terms, right? But who cares about them? They are inconsequential when I take the limit as n approaches infinity. And so on top, I have 4n squared. On bottom, I have 6n squared. That's really what this problem boils down to. Okay? So let's be clear about that. I think that's important. We don't worry about the rest of it. Okay, we really don't. Well, and of course, the n squareds cancel. And so this limit approaches 2/3, 4/6, which you'd be allowed to write 4/6 on the test. What does this tell us? Convergent, because? Less than 1. That's important. Say that it's less than 1. So now I can say that it converges by the ratio test. Okay, so again, algebraic manipulation. I'm so glad I teach this class now, because when I teach Algebra 2, I can tell these kids all the time, like, oh, you're going to get to calculus someday. You're going to need this algebra, because it gets kind of tricky. And if you're not good at algebra, these problems get really hard. Okay, so I got a couple other things to look at. We're not going to do any more problems. But let's kind of start kind of putting a bow on all these tests, all right? So these are some guides to when you do what, all right? So right away, step 1 is talking about the nth term test, right? Like, do a quick little check. Does the nth term approach 0 or not? If it doesn't, great, you're done, okay? And these are things we've talked about before. Just like when we talk about factoring. Take out a greatest common factor if you can, always. Check the nth term. See if you can use the nth term test to call it a day quickly. Is it a special kind of series? Is it geometric? Is it a p-series? Is it alternating? Then think about those tests, okay? Is your function, can you integrate it? Use integral test. Is it got a bunch of crappy notations in it? Try the ratio test. Does it look similar to another series that you're familiar with, or a comparison test? Is the algebra really ugly? Think about the limit comparison test, because things can cancel. Okay, this is in there somewhere in your book. I don't know exactly what page it's on, but same page. Okay, so that's good. And then the last thing is, okay, here they are, all the tests we're ever going to have. And so you've got like close to little less than 2 months to get really good on these, and we will continue to practice with them. But here they all are in one place, all right? And there's some little hints and things in there as well. But notice how they gave this sort of special series They put those at the beginning here. But, I mean, that's the order basically that we covered them, other than the ratio test. The ratio test was last. But other than that, they were the same. Okay. So this will be helpful. You talk about studying and making sure you get your stuff straight, and making sure you know when to use what and what conditions must exist and that kind of thing. This is a nice tool.